Dr. McMahon said, we're doing research on using quantum neural networks, or QNNs, quantum vision transformers, or QVTs, and the mathematical morphological reconstruction algorithms for brain tumor detection. And I'm Tiffany.
And I'm Ruby.
So brain tumors are the uncontrollable growth of cells that form an abnormal mass of tissue appearing in glioma, meningioma, and pituitary areas of the brain, and they can either be benign, meaning they're non-cancerous, or malignant, meaning they're cancerous. And they also come along with a variety of symptoms, including fluid blocks, brain pressure, internal bleeding, and loss of balance, vision, and memory. The rising rate of undiagnosed or inaccurate brain tumors is affected by current approaches which cannot detect the formation of these tissues early enough. And in fact, the National Brain Tumor Society states that 1 million Americans live with a brain tumor, where 94,309 people get a diagnosis, which includes a 35.7% relative survival rate in 2019 alone. Our team is approaching this inefficiency by compiling quantum environment applicable features of the MMR, or the mathematical morphological reconstruction algorithm, and the quantum convolutional neural network, or the QCNN, and its enhancer, the quantum vision transformer, to result in an early stage detection model with Skimage, TensorFlow, OpenCV2, and Qiskit. So currently, the most common form of tumor detection is done manually by radiologists with MRI scans.
They always
And that poses several issues as the amount of data has been increasing. It's become a lot more inefficient and tedious to manually sort through all of this data. And also, this form of detection relies heavily on the experience of radiologists, which can be really prone to error. And many areas also don't have the access to the resources or doctors necessary to perform this. So in an attempt to address these issues while accounting for accuracy and speed, there have been many recent and successful developments in deep learning approaches with CNN algorithms, which are also more accessible. And that leads to the basis of our research, which is to see if the MMR and the QCNN and QVT algorithms can outperform these CNN algorithms and see if introducing this quantum aspect gives us any advantage.
So first we started by collecting a data set of 1,711 tumors and 1,856 non-tumorous MRI images, which is split into an 80-20 training to testing ratio filled with various tumor shapes, types, and orientations. To start off the process, the images go through pre-processing, which is done in the skull stripping algorithm to isolate the brain. The output of the skull stripping acts as an input to the MMR, QCNN, and QVT algorithms. Our main goal is to extract the best features of the models to make a final model that increases the diversity for different kinds of tumors, since the MMR's principle is based on the analysis of shape and structure. In contrast, the QCNN and QVT are based on classification to recognize patterns in more complex data.
So the first step of this process is skull stripping. And skull stripping is a vital pre-processing step when analyzing brain MRIs for any purpose, including for tumor segmentation. In MRIs, the skull and the intracranial tissues, which aren't part of the brain, have the same bright intensity as the brain and its tissues, so it makes it harder to segment the brain if you don't first isolate it from the skull. Also, parts that do not belong in the brain add a lot of unnecessary noise and detail. So to skull strip, the image was binarized with adaptive Gaussian thresholding, and then two images were created to overlay on each other to determine the final edges for contouring. One mask was created through erosion, so taking away edges and removing noise, and the other through dilation, so preserving details and the general shape. And contouring is plotting the outlines of the segmented images, so after this we overlaid the two images by weighting them differently, 70-30, and it created an image with a good middle ground where it had enough edges and gaps and also maintained the picture's general contour with a good level of detail and not too much noise. And then the contours of the weighted image were blurred and combined, and when the medium blurred images were set, we identified the wanted contour by calculating the contour areas and choosing the largest area, which would be the brain contour. And the contour was used to make the final mask, which was applied to the original MRI image, producing the final brain stripped image ready for further processing. We also have made improvements on the skull stripping to help it run on MRIs of different orientations, lower contrast and quality, and tumors at the edge of the brain. So the tumors on the edge are much greater than intensity than the brain, so when they're on the edge, the skull stripping originally segmented them out too, but after improving it, we were able to isolate them. So as shown, the skull and intracranial tissues, or the border surrounding the brain, is removed in all four of these results. And removing the border just helps with tumor detection, since in most cases the tumor has the same color gradient as the border, and that makes the MMR and QNN algorithms more efficient in processing and spotting the tumor.
The next step in our algorithm is a mathematical morphological reconstruction algorithm, or MMR. We have gotten results for the MMR with an accuracy rate of 92% through repetitive ratio testing. MMR enhances and extracts image structures by iteratively combining dilation, erosion, and watershed thresholding operations throughout its iterative process. Dilation enlarges regions in an image, whereas erosion erodes the boundaries of regions in an image. The algorithm removes noise and artifacts by creating the marker image, which represents key points, and the mask image, based on the ROI and morphology operations for noise removal. Finally, watershed thresholding and segmentation is applied based on the concept of segmenting the ROI through a watershed line. The creation of marker and mask images guides the four-step reconstruction process. After fine-tuning noise removal with a peak signal-to-noise rate of 39.8, subsequent morphology operations are then deployed. The integration of watershed thresholding and segmentation yields a 92% accuracy rate in early-stage tumor detection. So these are some detection results from the MMR algorithm. The tumor is circled in red, and the size and location are visually accurate. To find the accuracy rate, the ratio of the values taken from 0 and 1, 1 equals true yes tumor, and 0 equals false yes tumor, and same thing was done for no tumors scans. And we plan to add this algorithm to our model because the tumor diversity in our data set is huge. And as the MMR is a less strong algorithm that doesn't go through expensive computation compared to our deep learning algorithms, we will use the scans with more vibrant tumor gray ranges for this model.
So the next part is the QNN algorithm. And at our stage in research, we finished building the model and we're just working on training and testing the model. So to start off, we'll be applying the architecture of a classical convolutional neural network in a quantum environment. And the CNN is a deep learning algorithm that feeds training data and detects patterns and process and classify our dataset. So classical CNN will consist of an input layer, some hidden layers, and an output layer as seen in the image. For example, here there's 2 hidden layers, but you can customize this towards your goal so you can have more or less. And in this image, these circles are perceptrons, which take an input and give an output. The algorithm's learning process adjusts these weights to detect different patterns. And to take a closer look at these hidden layers, in our case, we're primarily looking at convolutional and pooling layers. So the convolutional layer performs feature extraction, and then the pooling layer reduces the dimensionality of the MRI scan. And finally, the output layer classifies the scan as having a tumor or not having a tumor. So our QCNN will use classical data with quantum computing, meaning our quantum convolutional neural network will use a combination of the quantum computing concepts with the CNN that we just discussed. So like the classical CNN, we'll have convolutional and pooling layers, but we'll use qubits and quantum circuits instead. As you can see in this image, we plan to apply alternating convolutional and pooling layers on our quantum circuit. The secondary purpose of our research is to test if the QCNN has a better accuracy or speed than the classical CNN. So this QCNN algorithm will have 3 main parts. First, the encoding, then the processing, and finally measuring of the data, which just gives the output of the algorithm. So first, the encoding consists of converting the classical input data into a quantum circuit through angle encoding, which puts the qubits into superposition for parallel computation and applying rotation so that the data can be further processed. So next is in the processing step. It's similar to the CNN's hidden convolutional pooling layers, but it applies gates and entanglement with specific parameters. So the convolutional layer would involve the same feature extractions like the CNN, and the pooling layer would reduce the dimensions of the quantum circuit instead of the image while keeping the same data. So to do this, we encode the information from one qubit to the other, and once we do that, we can disregard the original qubit for the rest of the process. As you can see in this diagram here, the data from Q0 is encoded into Q2, and then the data from Q1 is encoded into Q3, and towards the end, we can disregard Q0 and Q1, and we're just left with Q2 and Q3. So this pooling would reduce the number of qubits in our circuit by half each time that we apply this layer. And in this case, we're reducing the quantum circuit from 4 qubits to 2 qubits, and we would continue to repeat this until we end up with 1 qubit, serving its purpose of smaller representation of the data without removing any important information. And lastly, the last step of the QCNN is to measure the output. So we measure the output of that single qubit through a softmax layer, which forms a probability of a specific state of that qubit, which then is translated to what that means classically, so whether or not there is a brain tumor.
So the last part of our model is the quantum vision transformers. Right now, we're working on training and testing. Before we delve into the QVT, let's analyze the classical model. Vision transformers, or VTs, are an image processing neural network-based architecture that has recently grown quickly by combining powerful techniques such as self-attention, allowing each element to make relationships with other elements through the comparison of significances for spatial information. The purpose of the QVT in our model is to overcome the challenges of the QCNN, such as capturing global relationships, increase scalability, positional embedding, and being restricted by a certain number of layers. We can go through a VT's process by referring to this layout. Firstly, vectors are extracted from the image, then split into 16 by 16 patches. These patches get embedded through linear projection. Then the purpose of these patch embeddings is for parallel computation and for retaining positional data, which will be processed by an encoder. The vision transformer encoder contains two main layers, the multi-self-attention layer and the MLP head, or multi-layer perceptron head. Before and after these layers are normalization and feed-forward layers, respectively. The purposes of these multiple layers is to make residual connections to prevent overfitting or generalizing new data and data loss. Before analyzing the multi-self-attention layer, we need to know what self-attention is. Self-attention is a mechanism in neural networks that allows the model to weigh all the parts of the input, not in just any localized regions like the CNNs. This means that the VT will compare every pixel with respect to every other pixel in the input. The importance of these inputs are stated in attention scores. Technically speaking, this concept is represented in the encoder through the Curie, key, and value parameters that calculates the attention scores, respectively, compute, compare, and represent each element in the sequence. The model splits the parameters in n ways and passes them into the attention head. Through the linear layer, these parameters contribute to the score by calculations with the information of the positional embeddings found earlier in the linear projection. At the end of the cycle, information from the Curie, key, and value parameters go to a single matrix for an attention score. After going through normalization and feed-forward layers, the data gets processed into the multi-layer perceptron head to introduce nonlinearity to refine relationships within the data. The attention score goes through a series of linear transformation and nonlinear activation through ReLU. The transformed attention score goes to the masked self-attention layer, or the decoder, where the model is trained to differ from the masked patches versus the normal to prevent overfitting. The transformed attention score goes to the classification head to get a result if a tumor is present in the image. Now that we understand the vision transformer's classical aspect, let's delve into what quantum can contribute to the vision transformer. So for the QVT, we're adapting a shallow quantum circuit, which is a quantum circuit with minimal depth, which can be used in the multi-self-attention and MLP head layer in the encoder. Specifically, we will be focusing on data loading methods such as quantum feature maps and compound matrices, and both provide the advantages of runtime and the number of model parameters. Aside from data loading, we are adapting quantum orthogonal layers, which replaces the MLP layer for quantum applied nonlinearity. In the first image, the patches are loaded into qubit states, which are represented as xi, processed through the quantum orthogonal layer, and additional variations of the data, like its inverse, are applied to prevent overfitting. This layer creates a probability state shown in the second image, which helps preserve the circuit data through matrix computation. Our next steps include completing the training and testing for the QCNN and QVT algorithms to compare these results to the CNN algorithm and MMRA algorithms to see if there's any noticeable advantage in terms of speed or accuracy. Finally, future possibilities to expand this project down the line would be to classify the types of brain tumors rather than simply detecting them, affecting the action speed for the doctor to initiate effective instruction at an early stage. We would also like to thank our advisor, Dr. McMahon, the ASDRP team, Alina C., another researcher who's helped us a lot with this project, and the rest of our group members. Here are our references. And thank you. Any questions?